In this lesson, we're going to be exploring what exactly a derivative is. To do that, first we're going to look at what an average rate of change is, and then we're going to look at what an instantaneous rate of change is, which is the definition of a derivative. So to answer the question over the top, what is a derivative? Keep this in mind, it's an instantaneous rate, oh no, I got that wrong. Instantaneous rate of change. But first of all, we're going to look at average rates of change, because this will help us understand how we find the instantaneous rate of change. Over to the left, I've got the graph y equals x squared. And I also want people to be comfortable with me writing it as f of x equals x squared. What we're going to do is find the average rate of change between x equals 3 and x equals 1. So we'll mark those on the graph. Here's x equals 1, it has the coordinates 1 and then 1 squared, which is 1. And then here is x equals 3. It has the coordinates 3 and then 3 squared, which is 9. So the average rate of change between these 2 points is simply the gradient of the triangle that I make from these 2 points. So I'll draw the triangle here in yellow. It's the gradient of that line. And the way we find the gradient of that line is the way we find any gradient. We say m is equal to rise over run. So the run, I'll do in red down here, and the rise, I'll do in blue. There we go. So let's work out those individually. The run is equal to, well, if this is 3 and this is 1, the run is equal to 3, take 1, so that's 2. The rise is a little trickier. It's equal to the height at this level, take away the height at this level, so that's 9, take away 1. Also written as f of 3, take away f of 1, because the height is the function, what comes out of the function. So that's equal to 8. Therefore, the average rate of change is equal to 8 on 2, so that's equal to 4. So that's how you find the average rate of change between 2 points. So bearing that in mind, let's look now for the second part of this lesson at instantaneous rates of change. And we'll say, what is the instantaneous rate of change at x equals 1. So we're picking a particular x value here. So we'll mark it on, not exactly in the same place, that's just a scale issue. It's got coordinates 1 on 1. 1, 1. And what we're trying to find is the gradient of the tangent that goes through here. Let's draw that tangent here in yellow. So we say, what is the gradient of that tangent? Now, at first, let's just estimate it. If I drew a line from this point to somewhere along the y equals x squared graph, then I'd have something that's pretty close to that tangent. And in fact, the closer along the curve I draw this triangle, so I drew one there, the closer the gradient of this side comes to being the gradient of the tangent. So if I can I can estimate the gradient of the tangent by the gradient of this side of the triangle. Let's mark in another point, just along. Now this is the tricky part to understand. I'm going to say, if this is the point 1, this is the point 1 plus h, where it just means I'm adding a little bit to 1, and therefore going a little bit further along the x-axis in this direction. So this has the coordinates 1 plus h, and then here's the really important part. Here's the reason we try to deal, as I said, in functions. The height of this point is f, 1 plus h. And this is very important you understand this before we continue, because this will influence the third part of this lesson. So now I can draw a triangle linking those 2 points. I'll put a nice straight tangent there. And the gradient of that red line is a very good approximation, especially if h is small, of the gradient of the tangent. So let's say what that gradient is. M is equal to rise over run. Now f1 plus h here, that is the total height, but it doesn't tell us the length of this line here. And the length of this line here, using the same method we worked out before, is f1 plus h, take away f1. That's the height. That's very important. If you don't understand it, think about it for a little bit before you continue. And the run here, well, the run is equal to 1 plus h, which is that level there, take away that level. So it's 1 plus h take 1, so it's run. So we had rise is equal to f x plus h take f1 plus h take f1, and the run is equal to h. So therefore m is equal to f1 plus h take f1 over h. Now here's where the maths actually does get tricky. I'll clear some space above before we continue. I said before, and this is the critical part of this bit of calculus, if h is very small, the approximation gets better. So we're going to use something that allows us to make h very small, and that is a limit. We say a limit as h approaches 0, so make h very small, of m, and m is equal to f1 plus h take f1 over h. That will be the gradient of the tangent. So we can actually simplify this expression because we know how to calculate f1 plus h. We have again the limit as h approaches 0 of, and f1 plus h is 1 plus h squared. Going back to this fact over here, f of x is equal to x squared. You just, if we're going to put 1 plus h inside the brackets there, we have to replace all the x's in the function by 1 plus h. So it's 1 plus h squared, take away f1, which is just 1 over h, which is, we expand out that bracket, lim h approaches 0, 1 plus 2h plus h squared, take 1 on h, which is equal to lim h approaches 0, 2h plus h squared on h, divide everything by h, so it's equal to limit, hang on, it's getting a bit crowded. We're going to move our working down here. Limit h approaches 0, 2 plus h, and since here we're not dividing by h, we can just say let h equal 0, so the gradient equals 2. So that's the instantaneous rate of change where x equals 1. So going back to that tangent we'd drawn before, at this point here, the gradient of that tangent will equal 2. Now let's look at how to find this for every single possible value of x all at once. I'll delete all this working, I'll leave it there for a few seconds. Okay, so now finding the instantaneous rate of change for any, we'll say any, x. So on the graph now, I'm not going to be so particular. I'm not going to choose x equals 1 or x equals 3. I'm just going to choose a point x along the x-axis. So this must have coordinates x, f of x. And I'm going to choose another point further along the x-axis, x plus h. So again, this is the difficult step. I'm just adding a little bit onto x, and the point above it must have the coordinates x plus h, that's the x value, and then f of x plus h. So if h were very small, then the 2 points will be very close to each other there, and instead of making a triangle that was a bad approximation for the tangent, which I'll try and draw here, it would make a triangle, as I'll show you, that's a very good approximation for that tangent. So even though this triangle I'm drawing is exaggerated in size, pretend it's very small. And we're trying to find the gradient of that red line. So again, we say, okay, we'll make a triangle out of it. The triangle's got a right angle. It's got this length here, rise, and this length here, run. And we say, okay, the gradient of that is equal to rise over run, which is equal to, well, this is the height fx plus h, and this is the height fx, so it's fx plus h take f of x. And what I'm going to do is just put a little green arrow there, and I'll fill in that line with green, so you know what it is. And then we've got the run, which is x plus h take away x. So I guess I'll write that in, x plus h take away x, which is equal to f x plus h take f of x over h. And again, I'll draw a purple arrow pointing to that part there. That is the length of this line here. So rise over run will give the gradient of the red line. So now let's make it very small. And to make it very small, we use the same machinery that we used before. Limit, let's pretend h is approaching 0, so h is very small. F x plus h take away f x on h. And we can expand this out. That's the limit h approaches 0 of x plus h squared take away x squared on h, which is equal to the limit as h approaches 0 of x squared plus 2xh plus h squared take away x squared. That's using the expansion that we're taught for quadratics. This is still on the screen, all over h, which is equal to limit h approaches 0. Hey look, this x squared value and this x squared value can cancel out, so it's 2xh plus h squared on h. Now we can divide everything by h. If we were dividing by 0, that would be a problem, but since we're using a limit, h only comes very close to 0. So this is equal to lim h approaches 0, 2x plus h, and since now we're no longer having to divide by 0, which would cause problems, we can say let h equals 0, lim h approaches 0, no, we can do away with the lim now. So this term here, which is m, is equal to just 2x plus 0, but the second part's obvious. So before we said, if we said x equals 1, we said m was equal to 2, and as you can see, that fits in the formula there. If you let x equal 1, m does equal 2. If we say wanted to find what is the derivative at x equals 16, then we'd say, well, the derivative, I've said m here, let's write it properly, it's just dy dx, or even f dash x. The derivative of f dash x, or the derivative of f of x at x of 16 is equal to 2 times 16, that's 32. So that's saying when x equals 16, if you drew a tangent along the graph, you would get a gradient of 32. Or, at that instant, dy dx, or the change in f of x over the change in x is equal to 32. Every function can be solved, every function's derivative can be found using this first principle here. It's very easy to get it out for a polynomial. It's more difficult to get it out for a sine of x or cos of x function, and square roots, it's even more difficult than that. So play around with it, try to understand it. It took me a few months to understand this when I first learned it, but this may come up in the exam, especially in multiple choice.